Welcome everybody to our next chapter, which is all about phases and phase change. I know, we are going to spend an entire chapter looking at solids, liquids, and gases, how they melt, how they freeze, how they boil, all that kind of good stuff. And yeah, it's actually going to take a whole chapter to do it, because we're not just going to look at like, oh, what's a solid? Yeah, it's a solid. What's a gas? We are going to look at it way down on the molecular level. We want to know what's happening to the particles. We want to know what's happening to the intermolecular forces of attraction, and we want to know what's happening to the energy, right? Because, I mean, if you think about it, that's what happens, that's what's involved when you go from a solid to a liquid to a gas, or a gas to a liquid, or a gas to a solid, or a solid to a gas, or all those kind of changes. That's to do with energy, right? So to make something change phase, to change from a solid to a liquid or a gas, you have to either add energy or you got to take energy away. You got to heat it up, or you got to cool it off, right? And in doing so, something happens. Something happens at some point that causes a phase change. And that's what we're going to dig into. Like, why is it that, okay, so water freezes at 0, right? So if you have a block of ice that's like -5 degrees, and I heat it up to -3 degrees, I'm adding heat. Why doesn't it melt then? Why does it have to be at that temperature for it to melt? All that kind of good stuff. So that's what we're going to look at in this chapter. But before we get too far into the whole actual phase change process, one of the things that we need to look at is this very strange and mysterious thing that still blows my brains out every time I try to think about it. It's like it's crazy stuff, and it's energy, right? So to look at how things change phase, the first thing we have to look at is energy, because remember, so to take a block of ice and to melt it, you got to add energy to melt it into water. And if you want to have water and you want to boil it into water vapor, you got to add heat, right? You got to add energy. Or if you have water and you want to freeze it, you got to take energy out of it. So what is this energy thing that we have to put into or take out of matter in order to make it change a phase? Well, it is actually not super easy to nail down what is energy, because boy, it's a crazy thing, this energy. But we are going to keep it simple, right? So energy is basically the ability to do work. That is what science defines energy as, right? And there are majillions of different kinds of energy. I mean, matter, this is a form of energy. It's like a condensed form of energy. Remember Einstein, E=mc²? Remember that whole thing? That equation shows us that matter is equivalent to energy, and energy is equivalent to matter. It's like two different forms of the exact same thing. So, okay, there's chemical energy, there's wind energy, there's solar energy. There's so many different kinds of energy, it's crazy. But we are going to stick to 2 kinds of energy, because there are only 2 major kinds of energy that are involved with phase change. And the 2 kinds are kinetic energy and potential energy. Now, kinetic energy, that is energy of motion, right? So if you want to experience kinetic energy, go have somebody throw a baseball at your face, and as the baseball impacts on your face, you'll experience that kinetic energy being imparted onto, your skull. You know what I'm saying? Now, the faster things move, right? The faster things move, the more energy they tend to have. Let's keep that in mind. So the other kind of energy that we're going to look at here is potential energy, and that's like this. Well, not like that, like this. Stored energy, right? Like if your battery is all the way up to here, if it's filled up like that, that means that you have a lot of potential energy. But if your battery is if it's way down like this, then you don't have much energy left, right? Stored energy, contained energy. Now for us, it's not necessarily going to be the same kind of energy as a battery, but actually sort of. It's all going to be about the energy of position, right? Like if you take a rock and you roll a rock all the way up a hill, that rock is going to have potential energy because of its position, right? This battery, it actually has potential energy because of the position of the chemicals that make up the battery. So potential energy is stored energy because of where the particles and where the things are. You got it? So those are our 2. We got kinetic energy, energy of motion, right? The slower you're moving, the less kinetic energy. The faster you move, the more energy. Bigger things tend to have more kinetic energy, right? So if you took a ping pong ball and you held it out like this and dropped it onto your toe, it would land on your toe and would not hurt so much. But if you took a bowling ball and dropped it on your toe, it's going to hurt more because there's more energy, more, it's like so much more because there's more mass, you know what I mean? So it's like taking a ping pong ball and throwing it at your face at 10 miles an hour versus throwing a baseball at your face at 10 miles an hour. So like mass is a part of it too, but so is like velocity. So if you took that same baseball and you threw it at your face at like half a mile an hour, you'd be like, hey. But if you threw it at like, you know, like these dudes in the major leagues that pitch at 100 miles an hour, and that hits you in the face, it's time for a new face. So that's kinetic, energy of motion. And potential energy, that is the like stored energy. Okay? Those are the two things that we're going to be digging into. And in a chemical reaction, right? And this is also chemical reactions and also physical changes too. We have exothermic, where you remember energy exits. And we have endothermic, where energy enters. And I'm going to add one more thing in there, which is activation energy. And I'm just throwing that out there now because we're going to be looking at activation energy a lot. And I just want us to, like, if we're talking about energy, we should also be talking about activation energy. And that's the energy needed to start the chemical reaction, right? There are spontaneous reactions that happen all by themselves. Like, let's say, a brush fire. Brush fires happen just fine once they're going, but they need a little bit of energy to get started, and that would be, your activation energy, and then stuff goes. So these are our two kinds of like directions of energy flow in reactions and also in phase change. Right? So we talked about in chemical reactions there being exothermic and there being endothermic. Well, also in phase change. We also have exothermic and endothermic in phase change. And remember, endothermic is when you put energy in. Right? So endothermic, heat enters. So anytime you're putting heat into something, that is an endothermic process. Exothermic means heat comes out. Anytime you take energy out of something, that's an exothermic process. For example, freezing water is exothermic because water is warmer than ice. So that means you have to take heat out of the ice or out of the water to turn it into ice, right? Same thing, only completely opposite direction. If you want to make ice and melt it into water, you got to add heat, right? You have to have energy entering your ice sample to melt it into water. You guys picking up what I'm putting down there? All right, so exothermic and endothermic happen for chemical reactions, and it happens for phase changes, right? Two totally different processes, but we use the same words because they mean the same thing. Exothermic, heat exits, and endothermic, heat enters. Good? Great! Let's look at weight, heat, and temperature. Well, it's weird that we have two words there because, isn't heat temperature and temperature heat? All right? We're just talking about exothermic and endothermic. We're talking about heat entering, and how do you know if heat is going into something? Well, the temperature goes up, right? Right? And how do you know if heat is exiting? Well, the temperature goes down. Well, if you notice, I'm using two separate words there, right? I'm not saying the heat goes into the sample and then the heat goes. No, I'm saying heat and temperature. I hope you picked up on that. Two different words because they are two very different things. That's why we have two different words for them. Most people, if you're just living your life, heat and temperature can be used like interchangeably, just fine. Problem is, when you enter the lab and you start really measuring and looking at things, you will find that heat and temperature, they're not the same thing, which is why we have two different words. And it turns out, here's the thing, heat is merely the transfer of energy. Okay, that's what the word heat means. Got it? So he can either enter something or he can exit something. Right? And then temperature measures how hot or how cold something is. Right? It is not a measure of how much energy is flowing. It's just kind of where thing is. Whereas heat is the energy transferred into an object. Does that make sense? So heat is the movement of energy, and the temperature measures how hot or cold something is. And we will define temperature a little bit better. But the thing is that these two things, heat, this transfer of energy, and temperature, like how hot or cold something feels, this is related by this thing that we call specific heat. Now, specific heat, or like specific heat capacity, there's a couple different ways to say it. But specific heat is a fundamental property of all things, all bits of matter, all substances, right? Just like density is a fundamental property of matter that you cannot observe just by looking at it. You have to pick it up and like get an idea of how big it is and how much it weighs. So density is there. It's like a part of what it is. It's an intrinsic quality that cannot be directly measured. Same thing with specific heat. Specific heat is a property of matter. It's fundamental, but it cannot be directly measured. Does that make sense? And it is what? It is the thing that links heat energy, the transfer of heat energy, and temperature, how hot or cold something feels. Does that make sense? Just like density is the thing that links volume and mass kind of together of a substance. Yeah? Great. So specifically, specific heat is the amount of energy needed to increase the temperature of 1 gram of a substance by 1 degree Celsius. Okay? So 1 gram of any substance by 1 degree centigrade. And it is absolutely unique to every substance. And you already know all about specific heat. And here's how. We're going to do like a little mental exercise, okay? We are going to get 2 fry pans. See, fry pan 1, fry pan 2. And in fry pan 1, we're going to fill it to about here with water. Okay, so this guy's going to get filled with water. And everything, by the way, is all magically exactly the same temperature. Okay, so 100%, this is all magical, theoretical, pretend time. If you need to close your eyes to think about it, you can do that too. Close your eyes. And then we are also going to light a magical fire underneath each one of these pans. The magical fire, because it's exactly identical, like 100% exactly the same. Okay, exactly the same pans, exactly the same fire, and then we're going to take our hands and put them right down onto each pan. And we're going to wait and see what happens. Now, the pan with the water, I guess, is it that one over there? That one? Over there? That one. This is not as easy as it looks. The one with the water, this one over here, right? This one. Just put your hand in the water, not all the way down to the bottom. So your hand just sits right on top of the water. And over on the other side, your hand goes right on top of that empty pan. And we're going to turn that magical fire up all the way to high. It's magical because it's exactly identical, right? The one on the left and right, they're perfectly the same. And you hold your hands there and wait to see what happens. Which hand gets lit up first? I'm going to bet that by now you know that an empty pan is going to get a lot hotter a lot faster than a pan with water, right? You know, it takes a long time for water to boil, or at least a few minutes, but it's like a couple of seconds for an empty pan to get like wicked hot. That is because metal and water have 2 completely different specific heats. Metal, like this one on this side, metal has a very, very small specific heat. In other words, it takes a teeny bit of energy to raise the temperature, like a lot. Whereas water, huge. Water has a relatively gigantic specific heat. In other words, it takes a massive chunk of energy to get water to change temperature. Which is why, if you have 2 magical fires that are exactly the same, an empty fry pan is going to get hotter a lot quicker than a fry pan that's filled with water. Because water has a much, much higher specific heat. Oh, and right here on table B, that's where you can go to find any and all of your specific heat questions, or like values, right? So specific heat capacity of water, right there it is. 4.18 joules per gram Kelvin. Yeah, we'll dig into what those units mean in a minute. And like I said, this is a fundamental property of all substances, and every substance has its own separate and unique specific heat. You can identify different metals and different substances and alloys by their specific heat. And even like liquid water, 4.184, well, ice is 2.03. So when I say every substance, it's also like every form of every substance has its own specific heat. And this heat energy, right, the thing that we're adding in or taking out, right, in order to make the temperature change, this is measured in what we call joules. Because of that guy, Lord Joules. He's the guy that like came up with this unit of measurement, so we called him, name it after him. Weird, old white guy in the history of science. Who would have thought? All right, so to give you an idea of like how much a joule is, it takes about 4 of these joules to raise 1 gram of water by 1 degree centigrade. So that's like about that much water cubed by 1 degree. It's not a huge amount of energy, but it turns out to be an adequate unit of measurement. Okay, and one other thing about heat and cold. Actually, cold isn't a thing. Cold is the absence of a thing. Heat, warmth, that's a thing. That's energy. Cold is just a state of less heat or energy. But anytime you have two things and they make contact with each other, heat will always go from hot to cold. For example, North Country winter, when it's like minus 30 degrees outside, all you got to do is step outside and you will experience how the heat leaves your body, the warm part, and goes out into the air, which is the cold part, right? It will always go from hot to cold. Always. It's like diffusion. It always goes from an area of high concentration to an area of low concentration. And if you have a hot object, that merely means that there's a relatively higher concentration of heat energy as compared to a cold object, which is relatively less, has something that has relatively less thermal energy. And just like with diffusion, it'll go from an area of high concentration to an area of low concentration. You guys picking up what I'm putting down? That is spectacular, because now it's time for the mathy stuff. Oh yeah! I don't think you can get away with like no mathiness here. Come on, man, science. We're going to science this thing out. So look, heat energy or thermal energy, right? This transfer of heat is calculated by this equation right here. Q equals mc delta T. Yeah? Q is mc delta T. And the way that we measure heat in the substance is with this thing right here. This is called a calorimeter. So what we do is we get a little sample right here, right? And these right here are they're just a wire, and it's kind of add a spark and like a little bit of heat. And this container right here, we pack with oxygen. I mean, it is like super high pressure oxygen, so that when we burn this, which is what we're going to do with this little coil, these little wires get super duper hot, and it lights up our sample. When we burn our sample, there's lots of oxygen left over. Remember balancing the chemical equations last chapter? What we do is we make sure that there's enough oxygen so that after the sample is all burned up, there's plenty of oxygen left. So everything gets burned completely. All the energy that we can possibly get out of that sample comes out. And what it does is it heats up this thing, that little container, and then that little container heats up all this water on the outside, and a little stir, just make sure everything gets stirred up nice and all the temperatures even and homogeneous. Then this little thermometer tells us the temperature change, right? Isn't that lovely? And then we come over here and use this equation. Q is the amount of energy. And I'm not really sure why they used Q. I think this is because they were running out of variables by that time. Now M, this is the mass of a sample, right? So M tells us how big is this sample that we are looking at. And C is the specific heat. And delta T is the change in temperature. Oh, also, C shows up the specific heat capacity or specific heat. It shows up as C, C sub P, lowercase c sub P. I don't know why they have so many. I really don't know. I really wish they just stuck with capital C, but I don't know why people do this to us, guys. I have no idea. So, what this equation is telling us is the amount of energy that you need to change this mass by this many degrees is related by this quantity. Or you can say, if I have 5 grams of this substance, like 5 grams, that substance specific heats, and I want to raise it by 10 degrees centigrade or Kelvin or whatever, how much energy do I have to have? This equation relates energy, mass, and temperature, given the specific heat of our unique substance. So as long as we know our specific heat, and we know like change in temperature and mass, we know how much heat it's going to take to cause that change. If we know how much energy we have and how much mass we have, we can predict the temperature change that we're going to see. So there's all kinds of things that we can do with this equation. Really what it's doing is relating mass, temperature, and energy with a specific substance. Are you guys picking up what I'm putting down? I certainly hope so. Because here we go. Because like why would I do something like with math unless, unless we were going to math. So here's the deal. Most of these things are going to be word problems, and you know how I feel about like looking at things and trying to read with numbers and words. It doesn't work well for me. So I always try to like take a word problem and make it not a word problem. The issue is that the whole world is like word problems. That's what reality actually gives you, right? You're never like at home going, and then like all of a sudden, boom, there's like a bunch of numbers in front of you. You have an issue, and then you got to figure out what you need to do to fix it. You guys get what I'm saying? So let's get the variables out. That way it's just numbers. It's so much easier than trying to do a word problem. So here is the question. How much energy? Well, remember, energy is Q, right? So I'm going to go Q equals question mark. That's because that's the variable that I'm looking for. So how much energy is needed to change 25 grams? So I know that mass is going to be 25 grams of water from 0 to 25. So delta T. Oh, and look right there. Again, because it's water, right? I go to my reference table, table B. There's my specific heat right there. That's awesome. But look, it was even given to me here, so I don't need to worry about it. So, wait. Since I only have 4.2, I'm going to use 4.2. So, here are my variables. I'm going to draw a line right here. And now, I'm going to choose the equation that fits my variables. Now, where am I going to get my equation from? Reference tables. Or, this one we pretty much know what it's going to be. But if you're not sure, because there's going to be a lot of equations by the end of the year, you go and look for the equation that uses these particular variables, right? You don't like choose the equation and then try to make the equation fit, because these these are what you have to work with. You know what I'm saying? So you choose something that has Q, M, delta T, and C, and then you write down the equation here. Got it? And then you enter the value. You do the substitution. Enter the values, like numbers, into the, what are those called? Variables. So Q, this is what we're looking for, equals 25 times 4.2 times 25. And my answer will be 2,625 joules. And here's the deal. This is called the flag method, and I'm going to expect you to use this. I will take points off if I don't see this particular method. I need to see the variables listed on the left-hand side. I need to see the equation listed out, and then I need to see the equation with substitution, where you put numbers or values into the variables, and then your answer can be down here. That's what I'm going to need to see from you guys. Hope you are like listening to this and not pausing and just like writing stuff down, because it's going to be a mess on this quiz if you don't hear me. You know what I'm saying? I insist on it because all of my students who do this do really, really well, and the ones who don't do this end up like getting lost and confused and stuff, which is just sad. So here's our next one. If gold is 0.13 joules per, I'd say, I guess that's the specific heat. It's the CP of gold. How much energy, well, here's my question mark, is needed to raise 5 grams of gold by 5 degrees centigrade? Oh, that's easy. It's like the exact same thing. Q equals MC delta T. I'm going to write down my equation because if you'll notice, the equation I chose incorporates all of my values. And then I'm going to substitute, what is it, 5? And now I do the math. You got it. I got it. I think you're going to get it too. You guys kind of picking up what I'm putting down there? If you'll notice, gold has a much lower or smaller specific heat. Look how small that specific heat is compared to water, which is 4. That's like more than 10. It's like 40 times greater, right? So that's why metals will heat a lot faster than water, because their specific heat is so super duper teeny. All right, let's keep going. What is this? Oh, that's a whole different ball of wax there. All right, so the CP is what we're looking for. What is this? Is the specific heat of iron if 22.5 joules of energy, well, that's Q, that's energy, are needed to raise a 5-gram sample from 20 to 30 degrees Celsius. Now look, here's the deal. I'm going to take a little side note here for like delta T. Delta T is always final minus initial, right? Because we're going from 20 to 30. So it's going to be 30 minus 20. That gives us 10. That's positive, right? That's because, so like when we're starting like this, here's our temperature. We're going from 20 thermometer, going 20 to 30, right? So temperature is going up. But what if perchance, what if instead of going from 20 to 30, what if we had something like in the opposite direction, where it's actually going down? What if we went from like 50 degrees Celsius to 25 degrees Celsius, right? So if that was the case, our first thermometer would look like this, right? Red stuff would be all the way up to 50. And then the second one would be way down here at 25. So we need to find some way to indicate that it's like that it's going down, that it's dropping, that it's leaving, right? So if we need to, like, if you have a bank account and you have money leaving your bank account, what do you do? Do you add or do you subtract? Well, you're going to subtract, of course. That negative sign means, in math, it actually means direction. Actually, in science, when you're applying it to science, the negative means leaving or like taking away or removing. Does that make sense? Which is why the way we find our change in temperature is always final minus, or we're going to take away the initial, and it's going to be the leftover. So in this case, it's going to be, if your initial is 50 and your final is 20, our delta T is going to be our final temperature minus our initial temperature, and it's going to equal minus 25 because the temperature has dropped. Does that make sense to you guys? And all that means is direction of energy flow, because in science, when you math, a positive or negative sign literally means direction. And when it comes to energy, it means positive means in, negative means out, just like a bank account. Do you guys understand what I'm saying? Excellent. I hope so. I'm sure you do. And if you don't, yeah, you're going to get it soon enough. You guys are all pretty smart. So let's come back to our problem. Sorry for that little like side rant thing there, but it's kind of important to like dial that in as soon as we can, because it can get a pain in the butt. So from 20 to 30, our delta T is a positive 10. So there's my line, QMC delta T. There's my equation. You dig? So now we're going to math. We're going to solve for C. And if we're multiplying on both sides, so if it's 5 times C, I'm going to divide both sides by 5. So I'm going to divide that by 5. Then I'm left with C times 10. And since it's times, I'm going to divide. So I'll divide both sides by 10. And math. Joules per, what is it, gram, Kelvin. Or actually, in this case, we said centigrade, so we'll say degrees centigrade. Lovely. Man, brilliant. Super duper easy. Next question. Ice is placed in water. what is the direction of heat flow? So I am going to insist on having some kind of like picture here for my brain. There is a cup. Here is the water. Here is an ice cube. There's the other ice cube. And here's maybe a third one blocking it. Okay. So let's think about this. Ice is always at 0 degrees centigrade. 0 degrees centigrade. Water, I don't know. What's water? Like nice cold water is probably like 10 degrees centigrade. I mean, just think about it, right? Water is always warmer than ice. So what is the direction of heat flow going to be? Remember, it always goes from hot to cold. So in this case, it'll go from the water to the ice. So it'll go from water to the ice. You may not say hot to cold. I know it goes hot to cold. You need to tell me from what thing to what thing. You dig what I'm saying? Of course you do. And we're done. The two things that we're going to work on associated with all of these notes are calculating joules and specific heat, but it's going to carry through with us the entire way. So, off you go. Thanks for sticking with me. I hope you guys have a spectacular day. I am totally going to do that, and I'll see you very soon.